This is our second video on angular momentum and its conservation. Before we do this, maybe we should introduce a new notation. It might be new for you, and it's this. Whenever we see a dot, sometimes they put a circle around the dot, that indicates a direction out of the page. In other words, that quantity, typically it's a vector, but not always, is coming out of the page at us. On the other hand, if we ever see an X, sometimes it's just an X, sometimes it's an X with a circle around it, that means that there is a quantity that is pointing into the page. And we're going to run into that here in this video. And perhaps the way you can remember that is if you can think of an arrow. And the arrowhead is a cone. It's a conical arrowhead. And then it's got feathers down here on the back end of it. If that arrow were flying right at you, wouldn't you see this picture in the upper left corner? You would see the point of the arrow, and then you would see the bottom edge of the cone. On the other hand, if the arrow is flying away from you, wouldn't you see something like what's in the upper right corner? You would see the feathers, and then maybe you would see the bottom of the arrowhead, that cone part of the arrowhead. So maybe that'll help you remember which way those notations refer to. Let's see what we've got here. We've got a platform, and it's rotating counterclockwise as viewed from above. That means that this edge of the platform is coming towards us. This edge of the platform is going away from us. And a bag is going to land on the platform. At impact, what's the direction of the horizontal force on each of these objects? Well, let's deal with the sandbag first. If you were the sandbag and you were falling down here, as soon as you hit this platform, wouldn't you experience a force into the page? And if the platform exerts a force on the sandbag into the page, then the sandbag exerts a force on the platform out of the page. Those forces that we just talked about here won't exert a net torque on the platform bag system. Why not? Because they are internal forces within the platform bag system. If we consider our system to be just, let's say, the platform, then when this bag hits, there would be a net torque on that platform. But if we consider the system to be the platform and the sandbag both, then there is no net torque on that system. So let's describe what happens here. The size of the variable that I've shown here, large I, large omega, small omega, indicates the magnitude. So here we have a diver. You've seen the Olympics, the divers. When their limbs are close to their torso and they're spinning, aren't they spinning quickly? And if they're all tucked up, don't they have a small moment of inertia? Then when they extend their legs and arms as they're entering the water, their rotation rate goes down, but now more of their mass is further from the rotational axis, so their moment of inertia has increased. What's happened here is that angular momentum has been conserved. The moment of inertia has increased, but the angular velocity has decreased. What about a rotating star that's in its normal form? It's shining brightly. It's rotating at some speed, usually. Our sun rotates, and it has a reasonably big moment of inertia, but then it collapses into a neutron star. Its moment of inertia is much, much tinier, and its rate of spin is much, much greater. Off the top of my head, I don't know these numbers, but you look it up if you want. The rate at which we believe neutron stars rotate, as I recall, is extremely large. Let's do a couple more cases here. Here we have a spinning ice skater. Her arms are stretched out horizontally, which means she's got a decent amount of mass that's far from the axis. a large moment of inertia. She's not spinning very quickly. Then she brings her arms close into her body, which means the mass is going to be closer to the rotational axis, which means the moment of inertia will go down, and then she starts spinning faster and faster and faster. And how about this? What about the platform that we met in part D? Should I put that picture back up here for you? Before the sandbag hits the platform and then after. Well, after, we have more mass that's farther from the axis that is rotating. See, this mass of the sandbag, it wasn't really part of the rotating system at first, but when it hits, it's going to contribute more now to the moment of inertia. So when it hits, we're going to have a bigger moment of inertia, and the rotation rate is going to slow down compared to what we had at the start. So in each case, what we're talking about here conceptually is that angular momentum is conserved.